Let's do something a little trickier. Electron deficient species. You're looking for the red flags, right? You don't get this very often, but these tend to be very, very reactive. They're not very happy, all right? So if you do the step 2, 6n plus 2 minus number of valence electrons, and you get a positive value, remember that can be one of 3 things. It can mean you have multiple bonds, right? Which every positive 2 value is a multiple bond or extra line. It could be an organic ring, which counts as a positive 2. Need at least 5 carbons for that. Or an electron deficient species. And what you're looking for, you get a positive value and you have one of these 2 criteria. You see boron, beryllium, or aluminum. All right? So beryllium, boron, and aluminum, they have a tendency, not always, but a tendency of having an electron deficiency. So either 4 electrons instead of 8 or 6 electrons instead of 8. So for every value, right? So if you end up with a plus 2, that means it's deficient by 2. So 8 minus 2 would be 6 electrons on it. If you had a positive 4 and you saw, boron, beryllium, or aluminum, then it would have 8 minus 4 or 4 electrons on it, right? And you'll see that's typical for one of those. So you'll see it with like 3 single bonds or 2 single bonds, and that's it. No lone pairs. You're like, well, that's weird. They tend to be highly reactive because they want to get 8 electrons. Now, it's either that, so look for those as your key. So whenever I see a positive value there, I'll immediately look for boron, beryllium, or aluminum. If I don't see them, I can eliminate that as an option. The other possible situation for an electron deficient species is that you have an odd number here, right? So like a positive 1 or a positive 3. You're like, whoa, we've never run into that yet. And the total number of valence electrons for that species is odd. Every example, if you look back that we've done, if you look at step 1, they've always been an even number, 40. 38, 12, 18. But what if it was 17 or 21 or 7 or 13? We've never run into that. That's an indicator that if you have an odd number of valence electrons total and you do step 2, 6n plus 2 minus number of valence electrons, you get like a positive 1 or something or a positive 3. You've got a special type of electron deficient species called a free radical where you have a single unpaired electron on there. So an unpaired electron. So you'll see one of the atoms in there might have 7 electrons or 5 or something, right? So it has, pair, and then just a single dot. You'll see just an electron dot by itself on one side. You're like, well, he would really love to pair up. So they're super, super reactive. They're called free radicals. There's a whole branch of chemistry on free radical chemistry, chemical procedures. It's kind of interesting. So let's do some examples and show you the thinking process. Here's your prototypical example you'll see probably in every textbook you ever read, because there's not that many, okay? Let's do it for boron trifluoride. Boron chemistry. Either you're crazy and love it, or you just run away as fast as you can. You can really hurt yourself with boron chemistry. What is the Lewis structure for BF3? Okay, we'll go do the steps. Are you getting bored with this yet? You're getting good at chemistry when it's just routine, same thing. Hit me again. Give me 2 million different possible molecules. Hit me again. Same thing over and over. You do these Lewis structures in just a minute or 2. Let's figure out the valence electrons. We got 1 boron. Whoa, we haven't had boron yet. So let's figure out how many valence electrons boron have. Boron. 1A, 2A, group 3A. So boron throws 3 into the pot. Whoop. And then we've got 3 fluorines. It's neutral, so we don't have to subtract the charge. Subtracting 0 is nothing. So 1, 2, 3, 4, 5, 6, 7. Fluorine is a halogen, giving us 7. So 3 times 7 is 21, plus 3 would be 24. 24 valence electrons. There you go. So now if that was odd, we'd go free radical, but it's even, so we're not necessarily going electron deficient, although you see the boron in there. Red flag, boron, beryllium, aluminum, boron, beryllium, aluminum, boron, beryllium, aluminum. Stick that in your brain. Look for those first. If you don't see those, you can eliminate electron deficiency and then look for carbon rings. If you don't see carbon rings, then it must be multiple bonds. That's the whole point. That's the elimination process. Look for electron deficient species first. If it's not one, if you get a positive value for the 6n plus 2, right? Do it in that order. This is the thinking process. No hydrogen, so 3, we got 4 atoms. So N is equal to 4. 4, 4, 4. So let's do 6 times 4 plus 2 minus 24. Let's see what we get. That's 24 plus 2 is 26 minus 24 equals positive 2. And we go, crud. That's one of three things, right? It's either electron deficient species, it's a carbon ring, or double bonds. Now, obviously, there's no carbon, so it can't be a carbon ring. But we see the boron. Do you see the trigger? Trigger, 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 trigger. So that's going to be an electron deficient species. And that boron atom is your trigger, right? You see, now if I don't see boron or beryllium or aluminum, first thing I look for, do you see boron, beryllium, aluminum? If it's not, and if this is an even number, if that's an odd number, that would be electron deficient. So if you see boron, beryllium, or aluminum, or that's odd, electron deficient. If you don't see those elements and that's even, wipe out electron deficient species as one of your options. Then look at how many carbons you have. If you have less than 5 carbons, it can't be a carbon ring. So that positive value must be due to multiple bonds, which is usually the case. But always eliminate electron deficient species and carbon rings first, then go to multiple bonds. Just don't go straight to multiple bonds every single time. So we can do this. We know we've got, now it's electron deficient by 2, so we're going to have, 8 minus 2 equals 6 electrons on it. All right? And boron's going to be our central atom because it's less electronegative than the fluorines. Fluorines are the top of the heap. They hate being central, right? So we're going to have this symmetric boron with 3 fluorines bonded to it. So let's put that in the middle there. Doesn't matter. You can put them top, bottom. It doesn't matter. This is just a Lewis structure. We're not looking at shape here. So we've got the 3 fluorines. So we've got 2, 4, 6. Do you see the 6? We do not put a lone pair there because that would give it 8, which doesn't match the electron deficiencies, right? We need 26 electrons for all single bonds. We only have 24. We're missing 2. See that? So we're going to have a disobeyed octet. So the fluorines are highly electronegative. They're hogs. They're going to complete their octets, right? So 2, 4, 6, 8. 2, 4, 6, 8 for that fluorine. 2, 4, 6, 8. So those halogens love to be terminal with 1 single bond and 3 lone pairs. And now you've got your electron deficiency on the boron. So let's see how many electrons we use. 2, 4, 6, 8, 10, 12, 14, 16, 18, 22. Well, let me do it again. 2, 4, 6, 8, 10, 12, 14, 16, 18, 22, 24. Whoa! 2, 4, 6, 8, 10, 12, 14, 16, 18, 22, 24, 26. Why do I keep getting 26? Oh, let me check this. Do you guys see why I keep getting 26? Because I can't count. I told you I missed the easy stuff. So funny. You have 8, 8, 8. 3 times 8 is 24, right? I keep getting 26. How do I keep getting 26? It's unbelievable. 2, 4, 6, 8, 10, 12, 14, 16, 18, 22, 24. What am I doing? It's so funny. 8, 16, 24. But I keep counting 26. I think I need some lunch. There's definitely 24 around that, but for some reason when I try to do it by 2s, I keep getting 26. So just slap me, please. Right? But we do know 24 equals 24. So hopefully you had fun with me attempting to count electrons, right? 4, 6, 8, 10, 12, 14, 16. That's unbelievable. Let's do a free radical. All right? Let's hit free radicals. All right, now that we're having fun attempting to count electrons by sets of 2s, right? Let's do the Lewis structure for OH. And hopefully you'll see in step 1 immediately that something's different. Something's very different about this one. Now, that's not OH minus. That's not the hydroxide ion. This is called the hydroxide radical, or hydroxyl. If you ever study atmospheric chemistry, you'll learn that's like the Pac-Man of the atmosphere, the cleanser, the oxidizer, right? There's not a lot up there, but it's very reactive. So a lot of pollutants that go up into the troposphere get munched on by the hydroxyl radical, which oxidizes it. And maybe we can see why when we look at the Lewis structure for this. So let's go ahead and do that. And hopefully I can count, properly. It's just hilarious on the last one. I can see the last one, I can see the 3 sets of 8. 8 times 3 is 24. 24 is 24. And then when I did it by 2s, somewhere my brain kept doing a trick getting 26. I did that like 6 times in a row. And then I did it again, I got 24. And I did it again, I got 26. That was just crazy weird. So anyway, it happens to the best of us sometimes. Let's do this. Well, this should be pretty easy, right? I got 1 oxygen. And those chalcogens are in group 6A, right? I've got 1 hydrogen, which is in group 1. So that's 7 valence electrons. Oh, so that is a key. This is odd, isn't it? An odd value means you have a free radical. Which means we are going to have an unpaired electron. Let's see where that happens. Well, I ran out of room there, so let's do this. What's N? We don't count the hydrogen, so N is equal to 1. Wow, this is a little bit easier. Maybe I won't screw this one up. Let's see. So 6 times 1 plus 2 minus 7. So 6 times 1 plus 2 is 8. 8 minus 7 equals positive 1. There you go. Right, we got a positive value. Well, that can't be a multiple bond because you need a plus 2. It can't be an organic ring because you need a plus 2. So that has to be an electron deficient species. So we're going to have 7 electrons. So one of the atoms, so gosh, I wonder which one. The oxygen or the hydrogen is going to have 7 electrons instead of 8. Let's see. So it's different than OH minus. So let's draw it. So we've got the oxygen and the hydrogen. We have to have at least a single bond, right? You have to have 2 electrons. So hydrogen will always have 2. You're not going to be electron deficient on hydrogen because that would just mean you have 1 electron in the bond. And that's not going to happen. So we've got that single bond. We don't have any double bonds, nothing like that, but we have an electron. So we need 7 electrons. So 2, 4, 6, 7. Do you see the electron deficiency right there? It's missing an electron, which makes it very, very reactive. This wants nothing but to take an electron from something. So if you breathe in an OH, whoop, it's going to be taking an electron. If it's attacking some pollutant up in the atmosphere, it's going to take its electron and create a free radical itself. Because if I take an electron from you and you had an even number, now you have an odd number, now you're a free radical. It's like this chain reaction that can happen. It's a whole branch of chemistry. So let's look on the next board and talk about why these are super reactive and what's happening. But does this make sense that that is an electron deficient species? 2, 4, 6, 7 equals 7. And we proved the electron deficiency. Free radical, baby. And also, if it picked up an electron, it would be OH minus, wouldn't it? Interesting. Okay. Hey, let's look at some real quick on why they're so reactive. I want you to think about this. This will come back in a full circle on us. So here's the hydroxyl radical, right? Or any free radical where you see some atom in it that is missing an electron, right? It has one purpose. I have one purpose in life: to take an electron to fill that missing gap right there. That's all it wants to do. Snag, 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 right? So that free radical species is super reactive, and it's going to take an electron away from some other species in order to complete that octet. That's its sole purpose, all right? Now, whether that species is some kind of pollutant in the atmosphere, right? So it takes an electron away from it and then it causes it to undergo some kind of some reaction process, which can change it to another species and remove that pollutant. That's why it's the cleanser of the atmosphere. What if you breathe that in? It could attack a protein, some other kind of molecule that's in your bloodstream. Oh, that can create some damage. Well, let's think about what's happening, right? Obviously, this ends up completing in its octet, so it's happy. But what happens to the species it took an electron away from? Oh no, it's a whole branch of chemistry. The other species that lost an electron go back to redox. Remember, that's electron. This is a redox reaction. It's electron transfer. So if I take an electron away from you, boink, I'm a free radical, boink, thank you very much. You lost a negative particle, which means your oxidation number went up. You were oxidized. Right? So again, if that happens in your body, that's called oxidative damage. So if you're jogging by the side of the road, there's a certain species that comes out of exhaust pipes, NO, which you could do. NO is a little trickier because you'll get, if you do it, you get a 6n plus 2 minus the number of valence electrons of a plus 3, which means it has a double bond and an electron deficient atom. Now, on my exams, I'm not going to give you anything that is two separate categories. It'll always be one. But the plus 3, plus 2 goes for a double bond between the nitrogen and oxygen. Right? So you've got the nitrogen with a double bond to the oxygen, right? That counts as a plus 2. Complete the octet, 2, 4, 6, and then an electron deficient species, right? You see that? So you get a plus 2 for the double bond, plus 1 for the free radical here. So this would be a total of plus 3 for your 6n plus 2 minus number of valence electrons there. So again, I'm not going to give you things where that's two, like you get an organic ring and double bonds, which is possible, right? And actually quite common in organic chemistry, but not on my test. Lab, I might hit you with one of those, or homework, but not on an exam. It's going to be just an organic ring, or just multiple bonds, or just electron deficient species. I won't give you something that maybe is an expanded octet and double bond, right? Because they would cancel out. It'd be too hard to predict, right? So anyway, you're breathing that in when you're jogging around. Well, if you breathe that in, not my specialty on the biochemical stuff and the physiology of it, but that can cause oxidative damage inside your body. And what are the long-term effects of that? Right? I actually read some papers and stuff where that is one of the leading theories for why we age and die is that free radical oxidative damage, right? Because you generate free radicals just metabolizing your food. So is that free radical damage that happens on a daily basis, a little bit, over time, you start kind of wearing down. And I don't know, that's physiology too much for me, right on? But let's say you want to minimize that damage, right? Obviously go live in a clean air environment, those kinds of things. Theoretically, minimize your eating. Oh, I don't know, can't prove that. But if you eat less, you metabolize less, would you generate fewer free radicals inside your... Maybe you'd live longer. I wonder if maybe there's some papers out there that study animals and stuff like that and feed them the same types of food, but just less for one than the other, but the same type of food. So you don't worry about saturated fats and all that kind of stuff, giving you heart attacks. But everything else being the same, just one gets more calories than the other. Do the ones that get fewer calories live longer? Maybe for, rat studies or something. Look it up. Maybe if that's an interesting thing to you, that would be a fun avenue of research to go down. But if you just want to continue your life and eat what you want to eat and live where you want to live and whatever, there is based on this, we can make a logical conclusion that if we could somehow prevent or minimize this oxidative damage, maybe we could live longer and be healthier. So if I wanted to stop oxidative damage or work against it, so what's the prefix for against? Anti. So you would take an antioxidant. Oh, like your vitamin C's or your vitamin E's, those kinds of things, right? And different types of herbals. So what you can do is take an antioxidant. Let's erase this, because I don't want to make a whole new board for this. So if you want, now again, there's articles that say they're not going to help at all. There's health articles that say they help. Do your research, and right, if you want to invest money in that, that's up to you. That's your call. Some people don't. They're perfectly healthy. You can get someone like George Burns who, sucks on stogies and cigarettes till he's 104, 105. Doesn't, there's a genetic factor as well. You could eat eggs every single day and have low cholesterol. Some people are like that. I eat oatmeal for a whole year and I have high cholesterol. Whatever, stupid liver, right? But you could take an antioxidant, right? Antioxidants. And others, right? Some of you are, nutrition experts, way more than me. Not my specialty. So say like a vitamin C, water soluble, fat soluble, that kind of stuff. Could that help minimize oxidative damage? I don't know. Something to think about. I'll open up that alleyway and let you run down it and see what happens. If you don't have any interest in that whatsoever, great! Just know how to do the Lewis structures. That's electron deficient species. So again, look for boron, beryllium, or aluminum, or you have an odd number of valence electrons and you end up with like a +1 or +3 or something like that for your 6n + 2. Those are your warning signs. You got it.